So yeah, my name is Nicolás Garavito Camargo. I'm a research fellow at the Center for Computational Astrophysics in the Flatiron here in New York. And it's really a pleasure to be here in this meeting. I know from this meeting, like since I was an undergrad student in Colombia, I always wanted to attend. So I really think that you gave us the opportunity to, attend remotely. I have enjoyed the talks. Yeah, so before I start talking about the Milky Way and the Large Magellanic Cloud, I just want to make a short announcement or like share some opportunities, because this is a Friends of Friends meeting, right? So I wanted to share a little bit about what the Flatiron Institute does, because it's a fairly young institute. It's like 6 years old, and it's basically a computational astrophysics institute. It has like 7 areas of research that you can find here. The one that I mainly focus is in galaxy formations and galactic dynamics. And what I wanted to share is that there are several opportunities for people to come and, for some periods of time. So if you're a professor, there are 2 ways that you can come, and one is sabbatical. So you can apply typically at the beginning of the year. And also there is another scholarship for professors, which is the IDEA Scholars, which is for professors that have done work in diversity and equity. And actually, Karin, which is at the conference, she was here last year, so you can ask her if you have questions. And if you're a PhD student, you can also come to something that is called the pre-doc program, which is basically a 6-month program where you can work with someone here, with a postdoc or a research scientist here at the Institute. So that was my advertisement. And if you have any questions, feel free to contact me, and I'll be happy to give you more information or advice. Okay. Now about the Large Magellanic Cloud, I guess I don't have to show you these pictures, and you are in the Southern Hemisphere. And I did my PhD in the Large Magellanic Cloud, but I have never seen it with my eyes. So for me, it's still, something that I would like to do, and another reason to come to the Friends of Friends meeting in a following year. Now, what I want to tell you today is that studying the dynamics of the Large Magellanic Cloud and the Milky Way has really changed how we now think what is the dynamical state of the galaxy. So before, we thought that we always model the Milky Way as an NFW profile. It's a rigid spherical sphere, and we always assume equilibrium. So today, the outline of my talk is going to be like the Milky Way is not in equilibrium in the presence of the Large Magellanic Cloud. And the second thing that I think is important is that we need to take into account when we try to place the Milky Way in a cosmological context. So when we compare the Milky Way in a cosmological simulation, depending on what questions are we interested, we might need to take into account the effects of the Large Magellanic Cloud. Okay, so of course, that is very big in the sky. It's the most massive satellite of the Milky Way. And actually, this is of course a cartoon, but showing that what is the size of the LMC if you put it next to the Milky Way. So the LMC is at 50 kpc, but if you put it side by side with the Milky Way, then you can start realize that it's a fairly big satellite galaxy, right? So the LMC is roughly 10 to 20% of the total mass of the Milky Way. We know this by methods as abundance matching, and we know the rotation curve of the LMC, so we can know what is the enclosed mass of the LMC at a given radius. So we have those 2 constraints of the total mass. So it's roughly 10 to 20% of the mass of the Milky Way, and it's at 50 kpc. And what changes, in the last 10 years, is that now we know that the LMC has to come in the first infall into the galaxy. Why is this? Because first, now we have better measurements of the proper motions, and we now know that the LMC is coming way more faster than we thought that it was coming before. So 80, 100 kilometers per second faster than we thought that it was coming from before. So a massive satellite coming with that speed is really hard to have it bound for several periods of time. So the most likely scenario is that it's coming for the first time. Now, you have a massive satellite coming for the first time into the galaxy, we expect, that it is inducing perturbations into the galaxy. So that's what I want to tell you today. So I studied this in a very simple case. I just made some idealized M-body simulations with gadget, and I think that so you can show an animation of the dramatic halos of the Milky Way and the LMC on the right. I also have a baryonic component, but I don't have hydrodynamics, so it's just pure M-body. And what you see here is just the LMC coming for the first time here on the top right. Actually, let me activate my laser here. So it's coming from the first time from the vital radius. And it arrived to the present day position, like more or less at this point in time. where we observe it. So both the positions and the velocity that we observe are are constrained by these simulations. I reproduce that basically. So it's a very simple simulation, but it allows us to understand very well the dynamics. The first thing that we realize is, I mean, we know this for a while, but is that what you're seeing in this movie is the overdensity of dark matter that the Large Magellanic Cloud enhances on the Milky Way halo. So this is just Milky Way halo particles overdensities in dark matter. So you see that as the LMC comes, it induces these large overdensities trailing the orbit of the LMC, and the disk here is at 0, 0, 0. What is this? This is something called the dark matter wake, which is really a manifestation of dynamical friction that Chandrasekhar taught us like 80 years ago, which is that if you have a massive perturber moving through a sea of particles, and this is the classical picture, it's a sea of particles of dark matter, these particles are gonna be gravitationally attracted to the perturber, and then they're gonna create this overdensity behind the satellite. And what this is gonna make is that there is an overdensity of mass, so this is gonna exchange angular momentum and energy from the satellite, and that's why satellite galaxies decay into galaxies, right? Because they're losing angular energy momentum. So if the Large Magellanic Cloud, is so massive, I think the dark matter wake that is inducing, and especially at the first infall, is the strongest. So it's our best chances to really look for the dark matter wakes in the stellar halo of the Milky Way. We should see something similar, like an overdensity of stars. So Charlie Conroy looked at data from Gaia and WISE to really have good measurements of distances of stars in the outer halo. So this is beyond 60 kpc. So this is an all-sky projection of stars, and here all the stars from Sagittarius were removed with proper motions from Gaia. And what you see here is in red, these are overdensities of stars in the outer halo, and in blue is underdensities. This is the location of the LMC and the SMC. You can see that behind the LMC there is this large overdensity, and in the north there is another overdensity that I'm going to talk about next. These are the simulations that I did before. I didn't do the simulations to reproduce these particular data sets, so it's just that you have a guidance on the of what we are looking at. So this is a tentative detection of some overdensity that might be the dark matter wake, but in its stellar counterpart behind the satellite. So this is promising because
2 minutes, please.
5 minutes?
2 minutes.
2 minutes. Okay, good. So this is pretty nice evidence that the galaxy is out of equilibrium. Now, in the last 2 minutes, the last thing that is happening is that you see that as the Milky Way, as the LMC comes, the Milky Way is moving, right? I mean, that's what we expect from an interaction, right? It cannot stay in the center. What happens, though, is that the outer parts of the halo cannot move at the same speed as the inner parts of the LMC, of the Milky Way, sorry. So this means that since we are in the disk of the galaxy, everything that we see in the outer halo is going to have a displacement both in positions and velocities of with respect to us. So it's not in equilibrium. And this was actually measured by Mike Peterson and Jorge Peñarrubia. And what they show with different tracers in the outer halo is that in these contours that you see here, that's the motion that the disk has with respect to the outer halo. And this motion in velocities is roughly 30 kilometers per second. So it's not small. These have consequences that I'm just going to briefly mention, I think, which is, I'm going to skip this movie, but it has some consequences for disequilibrium that I'm just going to go to my conclusions here, because the consequences are that any orbit that you want to compute for any outer halo star or globular cluster or satellite galaxy is going to be basically in another reference frame as the inner parts of the galaxy. So you really need to take into account that motion and that displacement in velocity. If you want to, for example, measure what is the mass of the Milky Way with dynamical estimates, so you want to use, for example, the timing argument or like Jeans equations, then you're going to be biased if you don't take into account this motion. And these last two things I didn't talk at all, but I'm just saying that the motion that I talk about, that the inner halo is moving with respect to the outer halo, it induces some correlation patterns in the outer halo when we are looking from inside. And especially like it induces orbital pole clustering to the same direction where we observe planes of satellites, like these planes of satellite rotating around the Milky Way. So this is very interesting, and And this is why at the beginning I say, like, it is really important that we understand the dynamics when we try to compare with cosmological simulations, because in cosmological simulations we don't see many planes of satellites, but if we look at systems that have massive satellites, then we see more of these planes of satellites, and it might be because of the effect that I just talked about. So with that, I'm going to conclude, and I'm happy to take any questions.
Thank you very much. Very nice simulations. So questions, please, in the auditorium, or okay, please, Augusto.
Hello, Nicolás.
Hi.
I have a question. I saw in your galactic map. So, what do you mask? Do you use mask in this exactly?
So we mask the disk of the galaxy, of course, and then we remove all the non-superstructure in the outer halo that we know that exists. Like, for example, Sagittarius stars that we know that are the outer halo is mainly made out of Sagittarius stars. So we remove those stars, and then we try to leave the stars that we think that are part of the smooth halo, although it's not very smooth. So we do it at our best, but there is certainly more substructure here.
Okay, thank you very much.
Thank you.
Okay, here, Nelson.
Hello, Nicolás. So also you mentioned at some point subhalo abundance matching, I think, but also measurements of the dynamics from HST. So I was wondering how well does the LMC fit subhalo abundance matching estimates, taking into account measurements, I guess.
Right. So you can use abundance matching just to know what is the mass of the LMC given its baryonic mass. But if you want to use subhalo abundance matching, then you can also predict how many satellites should the LMC bring during their info. And I think that the answer is around 5 to 6 satellite galaxies, which we actually then, with proper motion from Gaia, then we can really integrate the orbits of all the satellite galaxies in the Milky Way. And then we saw that at least 3 satellite galaxies, aside from the SMC, are coming with the LMC. So the LMC is coming as, it's like a group info, right, of the LMC, the SMC, and then 3 smaller satellite galaxies, maybe more. So that is in agreement with what we expect from subhalo abundance matching. Did that answer your question, Nelson?
Yes. Thank you very much.
Yeah, thank you.
Thank you. Please, Dante Miniti.
Hi, Nicolás. Could you briefly show the last couple of slides that you skipped?
Thank you, Dante. So one is consequences. This is just measurements of the mass. Or do you want to add a particular question here, or do you want me to briefly say something about this?
No. Just briefly summarize.
Good. Thanks, Dante. So this is just showing the mass of the local group, so Milky Way plus M31, using the timing argument. And then this is just as a function of the velocity between the outer halo of the Milky Way and the inner halo. So we know that more or less is at least 30 kilometers per second. So you can see that the mass that you get is at least 20% less than if you ignore this motion. This one is just showing orbits of different satellite galaxies of the Milky Way with different potentials, excluding the LMC or with the SMC. And then you see that the orbits are very different. So it's really important if we want to know the accretion history of satellite galaxies. And the last one, this is a bit complicated, but it's basically what you see here is the distribution of angular momentum of particles in a halo in isolation. So everything has to be isotropic, right? But if you have an LMC, but you don't include the LMC particles, just the Milky Way reacting to the LMC, you start to see that the orbital poles, so the direction of the angular momentum of the particles, is not isotropic anymore. They are just clustered to a particular direction, which is this one, the red one. And that's exactly what we observe, the clustering of orbital poles of satellite galaxies, of these planes of satellite problem. So yeah, it's very interesting to see that the LMC may have a role in forming these co-rotation patterns that we see in satellite galaxies.
Thank you
for giving more time.
Okay, thank you very much. Let's say thanks again,
Thank you.
Nicolás.